and they decided to go with 3 of them because somehow in every place where I go, when I present a talk, there is always somebody that is unhappy with some things that are related to machine learning, and they are complaining and all this stuff. So with 3 talks, I hope that at least one of the chunks is appreciated, or all of 3 they are not. So let's see what is going on this time. So anyway, so I will talk about three directions on which I'm working. They are about identification of deep neural networks. So it's very much an information-based type of analysis of identification of neural networks. And the second would be global optimization over manifolds. And the last one will be about mean field optimal control applied to the training of certain type of neural networks called NeurODEs. So this is more or less the 3 tales. Let's see how much I can present. So I start with the first tale about identification of deep feed-forward neural networks. And maybe I should start by saying that deep learning has become a successful approach for state-of-the-art applications such as image recognition, say speech and language recognition and translation, and somehow also mastering games. We know all about the stories of machine learning algorithms playing Go, beating humans on that, right? So we got to know all of this, right? But what is about machine learning, and in particular, what is about deep learning, right? So, well, it is better to start basic. What is a neuron? I mean, everybody speaks about very large, deep networks, but eventually somehow things are starting very simple with a neuron. So the neuron is a mathematical, the artificial neuron is a mathematical stylized version of the biological neuron. So a neuron gets some input and then somehow elaborate the input and eventually fire an output in a simple manner. And the way we stylize this by using mathematics is by considering so-called ridge type functions. So these functions are basically made of a scalar product of the input with respect to a weight that we may indicate with W here. Maybe there is a shift which is a scalar shifts, and to the result you apply a nonlinear, univariate nonlinear scalar function that is called activation function. And so you can embed the shift into the function and call it rho, and all of a sudden you have somehow that a neural network is nothing else than a ridge type of function, right? So, and this is the way somehow the artificial neuron is modeled. And yeah, but what is about neural networks? Well, ridge functions are simple functions, and they are used to create a sort of phase field separatrix. In particular, if your activation function is like a sort of hyperbolic tangent type of function, it is a sort of step-like function, right? Then if you see it, the ridge function is constant in orthogonal direction with respect to the weight. And so all of a sudden you create different hyperspaces, hyperplanes that are classified with different values, right? So this is what is happening. And if you do sums of such functions, you create tilings or tessellations of the space. And so all of a sudden you understand that you can create different kind of step-like functions. And because of that, you can approximate, say, continuous functions over somehow compact sets. And this is the so-called universal approximation theorem in neural network approximation, right? So this is a first example of neural networks. But if you want to create functions that they may be classifying and maybe a little bit more sophisticated in terms of the tilings, then what you can do is to compose such functions as well. So not only you create sums of functions like that, but you also compose them in an iterative fashion. And so you can create a sort of layers of scalar products with respect to the inputs, which means that if you stack them together, they are nothing else than applying certain matrices. And then you apply component-wise some of these shifted activation functions, and then you iterate the process, and what you obtain is what you can call a deep neural network, right? So as I said, the W's are called the weights of the network, and capital L is the number of layers of a network, and the tau L's are shifts that are coming into the activation functions, and so on and so on. Now, this is for practical applications. People are choosing the layers, determining the depth of the network and the size of the layers. So the number of neurons that you have per layer, which means the dimensions of the matrices. On the basis of heuristic consideration, now there are some optimization over also these parameters, including the size of the network and the size of the layers, by using the so-called AutoML. So it is a optimization over the architecture of the network. But in general, once these parameters are fixed, the ones that are open, that remain open, are the weight matrices and the biases or the shifts that need to be learned based on the training data. So how does it work? Well, you get some pairs of input and outputs, like an image and its corresponding label, like whether an image is about a cat or a dog. And you want to learn the parameters W and tau in such a way that the network is able to classify correctly certain inputs and certain outputs by minimizing the discrepancy of the output, right? So here you consider a sort of loss function that depends on the weights and the shifts, and what you do, you try to minimize this function. Due to the fact that networks are typically nonlinear objects, because the activation functions they are nonlinearities and so on. Of course, this optimization turned out to be extremely complicated, and in particular is non-convex, and so somehow all about the mystery of neural networks is very hidden in this optimization problem, right? So of course you can use other type of discrepancy, like the entropy, or somehow the relative entropy, or somehow the Wasserstein distance, or something like that, in order to create the discrepancies between outputs and expected outputs and the output of the network. So this is how it works. And the people are using mostly very simple methods to optimize these costs, typically first order methods like the gradient descent or stochastic gradient descent, or variations on the theme. And the reason is that they are very scalable methods. They may be able to escape the trap of saddle points in the landscape. And from time to time, they may even reach global minimization. And so that's why the people are using quite a lot gradient descent, but this creates some difficulties to understand what is going on in the case somehow things are not really so nice in the sense of a very complex non-convex landscape. There is a regime that is about somehow it's a so-called realizable regime, and the realizable regime is a regime where the number of training data is scaling as the number of free parameters of the network. So in a certain sense, this is a situation where, from a information point of view, you would expect that in order to identify a certain number of parameters, you need exactly the same amount of information. And so if the number of training data is of order is n, you would like n to be of the order of the at least of the order of the parameters of the network. And this is called the realizable regime because there are results that says that if the number of parameters are scaling morally as the number of training data, then there should be a network that interpolates the data, okay? So there is a way to realize the data by a certain network. As a matter of fact, somehow multiple networks will do the game, at least because of symmetry. For instance, we know that for symmetric activation functions, you can simply change the sign of the weights and the shifts, and you can obtain right away the same function, and therefore there are at least up to sign changes multiple networks that did give you the same function, right? But there are also other aspects like permutation of the order of the neurons can also be considered, and therefore you have automatically multiple global minimizers of this loss function simply just by symmetry, at least. In the overparametrized regime, where the number of free parameters of the network is exceeding significantly the number of data, then the loss landscape become quite less non-convex. So you can imagine that outside the region of the global minimizers, you have a relatively nice profile, okay? And that's why people prefer to try to train over-parameterized network by using gradient descent, because in that sense, it has been observed that it's a little bit easier to catch a global minimizer of the loss. Surprisingly, overparameterization and fitting does not cause overfitting, and this is due to the fact that most likely these optimization methods do perform an implicit regularization, so they do eventually promote low complexity networks. So that's some evidences about this situation. Okay, so in this, so while these results tells you that there is networks that are fitting the data in the realizable regime, and most of the people are trying to train very overly over-parameterized networks. The question is, how many different networks do fit really the data up to symmetry, and are we able to compute them explicitly by using a constructive algorithm without invoking a gradient descent? These are the questions that I may like to answer. And so, as I said, in the realizable regime, the landscape won't be that smooth, that convex-like, right? It will have a lot of kind of non-convexities appearing. And we don't know whether the network is unique up to symmetries. That's something that in general we don't know. And so it would be very nice to see whether we can identify it, right? So if there is only one network that does the job or not. And so all the story is about saying that there is only one network and that somehow the identification is robust, which means that if you change a little bit the training data, that the network that fits this data is changed a little bit, but not drastically. So if there is some robustness also in the stories, is a question that you may want to answer. Okay, the unique identifiability of networks has been considered in the literature over the past 3 decades. And starting with some work of Sussman and Albertini and others, and then there is a very, very interesting paper by Charles Pfefferman of 1994 that says the following. A generic fully connected deep neural network with activation function, the hyperbolic tangent, is uniquely identified by its output up to symmetries, okay? So there is no other network that will we realize the same output of a given network, okay? That's more or less what is coming up, of course, up to symmetries. and so on. And the way to prove it is by considering the network as a meromorphic function, starting from the fact that the hyperbolic tangent itself is a meromorphic function, it is hyperperiodic. And so it has some poles that are distributed in a periodic fashion on the complex plane. And if you create dilated and shifted versions of this hyperbolic tangent, the only thing that you do is by dilating and shifting also these poles. And if you are composing functions of this type, what you are actually do is by adding further poles. So you can see on the left of the picture here 2 poles of the hyperbolic tangent, and on the right is the composition of 2 hyperbolic tangents, and you can see that you simply have to sum up the poles and so on. But if you then compose dilated and shifted version of the hyperbolic tangent, what you get is an encoding of the shifts and the weights within the poles of this meromorphic function. And then comes a nice theorem that tells you that if 2 networks coincide on the Euclidean space, then their analytic extension essentially coincides in the complex space, and then necessarily they have the same pole, but since the pole are encoding basically the architecture of the network, then they must be the same network. That's more or less how it works. And there has been some generalization by Vlacic and Bylska in 2020, and so on and so on. But this is not yet the answer to the question that we had, in the sense that somehow a neural network remains fully determined by a finite number of parameters. And instead, somehow the theory of Efferman requires that you get to know every possible input and output of the network and know the output of the network in its full glory, right? But here we have a finite number of parameters to be determined. Unfortunately, already in the 90s, people like Stephen Judd and others, they showed that the problem of identification of neural networks from finite number of samples is an NP-hard problem. And so there seems to be little hope that you can determine a network with a finite number of parameters in a unique fashion without somehow incurring in some troubles with the complexity. But nevertheless, it is not at all expected that generically, so for somehow networks that are generated at random to a certain extent, that you would require really an infinite amount of training sample, and maybe you can find even situations where you can train with a number of samples that scales polynomially with the dimension and the size of the network, and that's a little bit the main results that I would like to present. Yet stochastic gradient descent won't converge to identification. So if you are in the realizable regime, you will observe that it's very, very difficult to get zero loss. So when you go in the overparameterized regime, as I said, you will get zero loss. So you will be able to minimize the loss landscape. But if you try to do that in the realizable regime, so in the regime where the number of samples scales as the complexity, that would be very difficult to achieve. And so in general, you don't identify things with gradient descent. So you need something else. Okay, so this is the kind of, this is a sort of meta theorem that for which we had the different instances in the past, starting from the 1 neuron case to the 1-layer neural network case, up to 2-layer neural network case, up to the deep neural network. So it was a sort of a sequence of different papers that we wrote that end up with what I'm presenting today. And so in this theorem, it says that for genetic networks of complexity W bar, with smooth activation functions, they can be stably constructively identified from a number of samples that may be actively chosen. So if you have a network and you sample this network and then you try to recover the network from the samples, then you can do it in a constructive and stable fashion. And that's a bit the result that I'm going to present, which is a bit surprising because somehow it tells you that, yes, in general, the problem is NP-hard, but if you go on a generic situation where you may generate the network at random, then basically you can recover it in a constructive way. And the algorithm that we will use won't be affected by the curse of dimensionality so it will be always polynomial in the dimensionality and so on. Okay, the way we do that, we learn the parameters of in particular the weights and the shifts in a two-step fashion. The first, we try to learn the weights by using second-order derivative information of the network and identifying the so-called entangled weights matrices, which I'm going to explain to you in a moment. And then once you have the weights of the networks, there are other parameters like signs, scalings, and shifts of the network that can be identified by gradient descent. So you resume gradient descent, but in that case, you will get zero loss. And so that's more or less what what is the way to go. At this point, I would like to ask you whether you have questions before I get into some of the technicalities.
Sorry, Massimo, may I ask a very, very general question? So
yes.
what is the motivation? I heard a lot about this identifiability, but what is the motivation of wanting to identify the parameters of a neural network?
Okay, so there are many reasons for that. The first is compressing a network. So in case you would like to, you have a network that is very, very large, overly parameterized, and still you would like to find a smaller network that can approximate this one. You can try to identify this smaller network that does the job. And and what you can expect is that this network has a number of parameters that is at least as the number of samples that you take out of the previous network. But somehow creating a correct identification from the samples to the weights, and also a unique relationship, a map between these two things that is sufficiently smooth, so it is relatively robust and so on. It tells you that there is an encoding going on. So you're encoding the input into the weights, and you have some control on this encoding. If you had not a unique map from the way you map the input data into the weights, then you lose ability of saying something about these weights. They become, yes, they encode things, but they do it in a non-unique fashion, and so it's a little bit less clear what they contain as an information and where the information has been spread all over these different weights. So it goes in the direction of trying to see whether there is any way to interpret somehow this encoding done by a network of the data, and also whether this has some continuity, and this continuity is quite important in order to avoid somehow that by simple jittering a little bit the data, you produce completely different networks, and so on and so on. So a stable identification of a network is an effort to try to see whether you can embed some correct understanding of how the data are encoded in the weights, and whether you can also embed a little bit of robustness additionally. I don't know whether I answered your question.
Yes, thank you very much. I also take the chance to say to people, they can also raise their hand or type in the chat, and we read the questions at the end of the talk, or well, as they appear. Okay, thanks, Massimo.
Are there further questions?
Could I ask a question?
Yes.
So if I understand correctly, this identification is like you look if another network with the same parameter or with different parameters gives the exact same output. But
with the same size,
right.
Of course, there will be networks that are larger than will do the job, most likely. Okay. But you ask yourself whether there is another network with the same architecture that does the job.
Okay, so my question then is, do you think that this task would be a little bit easier if you were to relax, for example, that you allowed some discrepancy, like an epsilon?
That's exactly what I'm saying. You would like that it is also robust, that even if there is another network, that network won't be too far from the one that you.
I see. No,
sampled,
thank you very much.
You know? Yeah. There is another question from.
Yeah, is it also kind of a question to find the minimal size network?
Exactly.
Okay.
Exactly. It is also that. It's exactly also that. It's a compressing networks as well.
Thank you.
Okay, let's move on. So it's a formal definition of what is a feed-forward neural network, how these weights look like, how iteratively you can define the network, and most of all, somehow, how do you define somehow this little m parameter, which is the sum of the number of neurons of each layer, okay? In this setting, we also consider vector-valued networks, and so we have multiple outputs, not only one output. So you would like to consider multiple channels or multiple components of the network itself. Okay, this is all about neural networks in the definition that we consider. I display some of the networks here that are considered in this definition and in our theory. They can be something of variable size in terms of individual layers with some vector valued output. They could be rectangular like network or stuff like that. You with me? Okay. Now we start with the question, how can we identify this network? The first thing that I would like to show you is a reparameterization result by what we call entangled weights. So entangled weights are nothing else than compositions of weight matrices where certain permutations may come into the game, and certain diagonal matrix DIs and SJs may come into the game. Okay, so we call an entangled matrix a matrix that do have this particular decomposition for some diagonal matrix Ds, some diagonal matrix S's, and some permutation matrices. Okay, it's just put it together these weights. Okay, it's new matrices that have this decomposition. Now let's assume that an oracle, somebody, gave us matrices of this kind, and we assume that a certain genericity assumption is fulfilled, which means that these matrices have full rank. Then we can construct new weights that are built by using these entangled weight matrices and the use of these somehow diagonal matrices that are missing. And the network that we construct by using these new weights and by at most changing the order of the neurons will be the same network up to permutation of the output. Okay, so in other words, as soon as I'm able to find these entangled matrices and I am provided with these scaling and dilation matrices and the shifts, then I have the network. Okay, it's just an algebraic trick. You with me? Okay, so in other words, I can identify the network. I have the network as soon as I have entangled weight matrices, and on top of that, I have this diagonal information, diagonal matrices, and these shifts. And so the first issue is, how can I gain these entangled weights? Well, an example of entangled weights are matrices where the famous diagonal, one of the diagonal matrices is given by the diagonal matrix of taking the activation function, say, first derivative evaluated in a certain input, and composing the weights according to this decomposition. And for every different input x, this is actually a collection of entangled weights matrices. And so I can generate many matrices of this type depending on a certain input. How do these matrices come out somehow? How can I generate these matrices? How can I produce these matrices? And that's a remarkable fact, that if you consider the Hessian, really the second derivatives, say, of the pth output component fp of the network. So the network is a vector value function. I look at one component of it, I take the Hessian of it, okay? Then the Hessian is decomposed in terms of a sort of singular value decomposition like decomposition, and the vectors that are made of the columns of these matrices are precisely sort of vectors that you can use to create rank 1 decompositions of this Hessian. And these rank 1 decompositions are, of course, not orthogonal, so they are not really singular value decompositions, but they were orthogonal, then you would simply be able to generate these matrices by using the singular value decomposition of the Hessian of the network. Okay, so that's a fact. And the trouble is that since these decompositions are not orthogonal, it won't be simple to extract this decomposition, and the singular value decomposition of the Hessian won't have this structure in general. Okay, so you cannot simply pick the singular value decomposition and use that, but you have to use this decomposition. But it's hard to extract these guys by using one Hessian. And now comes a very interesting observation, that the mapping the input into these matrices it's a smooth function. It's a very nice Lipschitz function. So the mapping x into these matrices is Lipschitz, and therefore if we sample the Hessians from a certain distribution tightly concentrated around a certain point x, then the Hessians would concentrate around a certain subspace spanned by very specific rank 1 matrices. And the rank 1 matrices are exactly the entangled weights sampled up at x star. So if we generate multiple points around x star and we compute the Hessians and we try to understand where these Hessians are concentrated as a matrices, it turns out they are concentrated around the span of these rank 1 matrices. Okay, and so it is possible by doing PCA or singular value decomposition on this point cloud of Hessians, you can get an approximation of this subspace W. And so being able to identify certain entangled weights is translated into the problem of identifying rank 1 matrices in a space spanned by themselves. And so we do have this subspace that is the span of these rank 1 matrices. And we do a couple of approximations, a couple of assumptions. We assume to have been able to find a subspace W hat that is very close to the given space, in the sense that the orthogonal projections are not too far, and there is a delta distortion about them. And we assume that these weights, W1, Wm, they do form a frame, so-called frame. They are not linearly independent, they are not orthogonal, but they might be overly, so they might be a linearly dependent system, but they are sufficiently spread. And here it comes one more genericity assumption, say, if they were generated at random, they will be nicely distributed in a certain sense. And that's the second assumption that we make, and so on. And so the idea is how to find approximations to these rank 1 matrices within the subspace W hat or in the near of it. And the way you do that, you basically solve the following optimization problem of the sphere. You try to find a rank 1 matrix that is projected onto W hat, has the maximal Frobenius norm or even the maximal spectral norm. So the idea is that you would get here, you would like to reach 1 as a value here. And it turns out that somehow under these assumptions that the space has been well identified and the vectors are sufficiently well spread, then this optimization problem is able to identify them. I'm not getting into the details, the technical explanation of the thing, but basically by solving this problem, you will be able to identify the weights. Okay, how do you solve that problem? Well, you can use a sort of steepest ascent method that it can be implemented very easily. And it's possible to prove that if you start from random initial conditions, this algorithm is able to achieve the global maximum. And nevertheless, it's always converged to a steady state of the problem. And so somehow we do have these results. And if you really run this algorithm with different parameters of the network and so on, and you ask how many times you are able to identify correctly the parameters, in certain regimes with enough information, you will be able to identify all the vectors exactly and robustly. Okay, that's exactly what is going on here, right? So, as I said, once we have entangled weight matrices, we can identify the network if the rest of the parameters is at your disposal somehow. In particular, the shifts and this diagonal information, and so on and so on. So how can we identify the remaining parameters? We do it by least squares. So we simply assume to use the given entangled weights as an input, and we try to identify the shifts and the remaining parameters by gradient descent. And what you can prove is that you can observe numerically, first of all, and prove in certain cases that actually gradient descent will converge to zero loss. So basically you converge to the right network. And that's what is going on here. Okay, so you can also compare the results with gradient descent, what is happening with stochastic gradient descent. And what you can see is that in certain cases, for certain kind of architecture, stochastic gradient descent can never really be able to reach zero loss. It can reduce certainly the loss, but not really converge to zero. While this technique that is actually designed to compute exactly the weights, it does do the job. Okay, that's more or less end of this first tale. As I said, it's an impossible task to present all of them. Let's see whether I can do it. But maybe I will take 1 or 2 questions for this part, and then I'll try to continue with other two tales and see how much time I can dedicate to them.
Can I ask just a very quick question? When you looked at the Hessian after the reparameterization, X was the data. So at some point a little bit before.
So you are allowed to use active sampling. So we are not starting with an arbitrary distribution of X, and we can allow ourselves to choose the input. So I'm not claiming that this will work for any possible distribution. You actively choose where you sample X and how you approximate the Hessians.
But somehow μx is not related somehow to some distribution that then when you take the loss function and for large n somehow you want this to behave some way.
No, so you are given you are allowed to query a network. Okay, you're allowed to query a network, and you decide where to query it. Okay. The question is, even if you can query a network and you can decide where to query, can you do it in a way that you can reconstruct the network exactly?
Right. So μx here is not arbitrary. There is a particular design choice.
It's a particular design. It's an active sample.
Okay.
So in the initial theorem, I said that the number of possibly actively chosen samples.
Right.
Okay. So, but it tells you that there is a set of samples for which the network is completely and uniquely identified, right? So it's a sort of information theory type of issue.
Thank you very much.
Okay, so if there are no further questions on this part, of course you can ask later on further questions and move on to a second.
Maybe could I also ask you a question?
Yeah, Greg.
So
please.
with the stochastic gradient descent algorithm that you're using here, does it make any difference if you use first order or second order dynamics?
So if you add a little bit of inertia, you mean?
Yes.
Well, certainly it can help. You might have some better effects or stuff like that. We didn't really try. We simply wanted to. I do believe that it could help, but it could not necessarily solve the problem, especially when the network architecture become a little bit more sophisticated. We believe that in this regime, the landscape becomes so complex that even with a little bit of inertia, things might not work anyway. So we didn't try, but I don't believe that it would solve right away the problem. Plus, we don't have guarantees for that, right? So even if you have such inertia, you have to prove then that you converge to global minimizer.
Mm-hmm.
Well, we have a sort of constructed methods to prove that you converge to the exact weights, of course, up to permutations and signs.
Thank you.
Okay, so the second tale is about global optimization. So we have seen that here, eventually, you are obliged to perform some optimization, which is non-convex, and it is defined on a manifold. Okay, this is an example of where these kind of things come up, but there are many situations where somehow non-convex optimization with constraints is considered. And in the past, people have been using more than these first order methods. They have been using a lot of other methods like meta-heuristics. And for that, I mean, many methods like simplest heuristics, evolutionary programming, simulated annealing, up to particle swarm optimization. These methods do show tremendous empirical results, but still lack some strong guarantees of robust convergence to global minimizers. In some cases, there is some theory that explains what is going on. Sometimes the theory is not quantitative. And so because of that, in the past years, there's been some recent work by Pinot and others, and later by Jose Antonio Carrillo and others, that proposed a so-called consensus-based optimization, which is a bit a fusion between simulated annealing and particle swarm optimization. And therefore, it is a derivative-free method based on an instantaneous stochastic and deterministic decisions that allow a multi-particle to find consensus about the location of the global minimizer. But the good part of the story is that it is designed to be analyzed. So basically, these methods are designed somehow with concepts that are made for them to converge to the global minimizer, but they are hard to analyze, and this is has been designed to be analyzed. And so the way to go is that the evolution is interpreted as a discretization in time of a system of stochastic differential equations. Most large particle limit is described by the solution of a deterministic partial differential equation, and the large time behavior of the solution is then somehow addressed by classical calculus methods, and this is somehow providing a rigorous understanding of what is going on. This is more or less how meta-heuristics work. So you see that this is a function with multiple local minimizers that can fool any first-order method, right? But here, in a certain sense, we have a multiple particle scheme that eventually learn where the global minimizer is and eventually converge pretty rapidly to this global minimizer. So this is very surprising dynamics, but actually the definition is very simple. So let's assume that we want to minimize a certain function E over the flat, over the Euclidean space, by using multiple particles V1, Vn, whose empirical measure is given by rho n. Then these particles are have an evolution in time where there is a drift towards an instantaneous consensus point that we call the alpha, which I'm going to describe in a moment. And they are perturbed by a sort of stochastic term that represent somehow an exploration that the particles do that is very, very strong if the particle did not converge to the consensus point yet. So the consensus point V alpha is computed as a weighted center of mass according to the Gibbs weight in a certain sense. So you basically give more mass to the particles that have a smaller value of E, and you give little mass to the particles that are far away from the minimizer, and therefore you expect V alpha to be very close to V star somehow. And this is a bit the dynamics. And as I said, the remarkable thing of this dynamics is that it does converge to the global minimizer, but why? Why does it do the job? Well, as a matter of fact, if you pick certain initial conditions and you fix them, and then you generate other particles at random, and then you observe what these particles do typically starting from these points, and then you take the average trajectory that they do, it turns out that the trajectory that they do is very trivial. It's going right straight to the global minimizer. What does it mean? It means that on average, this method is performing the gradient descent of the quadratic function V minus V star squared, right? So this method looks quite sophisticated, but on average, what it does is convexifying the problem in a canonical way, so by creating a quadratic function, and then what you do, you are following the gradient of this function right away, straight. That's what is going on, independently of how non-convex the function at the beginning was that you wanted to minimize. And so more or less, this is the main result. It tells you that if your function is mildly smooth, so it is locally Lipschitz, and the level sets are indicators of where you are with respect to the global minimizer, then on average, the behavior will be the minimization of the quadratic distance to the global minimizer. So in particular, you can claim that these methods converge globally in mean field law. Okay, so whatever initial condition you start, you will always follow this gradient of the parabolic somehow function. Okay, so that's what is going on, and as I said, the way to prove this is by consider the iteration as a discretization in time of this stochastic differential equation system, that it can be proven to be approximable by a sort of propagation of chaos phenomenon by the monoparticle dynamics given by this equation, where instead of having the empirical measure here, you have the law of this self-consistent equation, and the law itself somehow it does approximate, it does solve a certain partial differential equation. But the informal explanation is that if you fix the initial condition and you observe what happens to the average trajectory behave like a gradient descent towards the global minimizer up to a discrepancy that you can see here that tells you it is the discrepancy between the guessed somehow consensus point and the global minimizer. Then what you can do is by proving that this consensus point is actually very close to the global minimizer all the time, okay? And this is due to the combination of the so-called Laplace principle with the fact that we are requiring that the level sets of the function are indicator of the distance from the global minimizer. And because of this persistent approximation of the global minimizer, you actually have this gradient descent behavior. Okay, I'm not going to the details of the formal explanation of this. Okay, I just mentioned that these methods can be generalized to manifolds. We did it on compact hypersurfaces, for instance, the sphere and the torus. So basically, what you can see is something like that. So you can minimize function globally on the torus, but similarly, you can have a dynamics for the sphere, and here you can see certain kind of functions minimized on the sphere. Some relatively simple functions with a very pronounced global minimizer, but also functions that are more difficult where the global minimizer is less somehow, it's easy to find. And we have, of course, some results of convergence also for these cases, and that's more or less the second tail story. Okay, I am stopping here, I would say. There would be a third tail, but I don't believe that we have time for that, unless you really want to do the pain of another 5-6 minutes. And so I'm open either to questions or to anything you suggest to do at this point.
I don't know, Massimo. If there are no questions, I think you can go on. If it's really 6 minutes and if people are busy, maybe they can just log off and those who are interested may stay a few minutes. If it's not that much, I mean, if that's okay for you.
Yep. Okay, so now we saw one way to train neural networks in the sense of identifying them actually. The deeper is a network, the harder become to train it. And so people understood that, and the reason why it become harder to train is that sometimes the gradient descent gets stuck, or it is subjected to very pathological situation like gradients vanishing or gradients exploding. And because of that, they observed that if you insert certain kind of skip connections, what they call them skipping connections, which means that not only you process the input of a layer and then you pass it to the next layer, but you combine the input of a layer with the output of the layer and you pass it on. If you do this kind of operation, so skipping in a certain sense one layer and adding the result to the output of that layer, would stabilize the behavior of the gradient descent. In particular, the gradients would become a little bit less pathological. And this has been observed, and this allowed to train very, very deep network, but nobody really knew how to motivate this up to certain phenomenological or somehow intuitive explanations. So then it came up that somehow Rutotto and Haber, and then later on also Venan A and other colleagues, or Venan, they interpreted these networks as Euler scheme approximation of systems of ODEs that are controlled by the weights of the network itself. So we understood that the network is a typical application of activation functions to matrices applying to inputs, right? And so what they propose is to consider actually ODEs of a certain kind, okay, with certain kind of field of somehow of the ODE, and the ODEs are somehow controlled and represent somehow the training of a neural network is then interpreted as a classical optimal control problem. Venan provided a so-called mean field optimal control interpretation in the language of stochastic control. How does it work? So you basically have pairs of input and output jointly distributed according to a certain probability distribution mu. And then you fix a depth that in this case is a time horizon. And then what you do is minimizing the following stochastic optimal control problem. You solve the following stochastic optimal control problem, where you generate at random x0 as an initial condition of the ODE. And then at the time xt, you wanted that the output of the network is not far from the randomized choice of y0. And as I said, x0 and y0 come as pairs jointly distributed according to a certain mu0. And so what you do, you are trying to minimize the loss, which is L, by taking the expected value with respect to all input and output pairs. And so basically, Venan A studied this optimal control problem in the sense of in this formulation of stochastic optimal control. Recently, I took this problem and I reformulated in a measure theoretical transport sense, and this is the way to go. So if you have now, you augment this ODE with a fictitious ODE of the output, where you get a constant somehow dynamics with initial data x0, y0, okay, distributed with mu0. Then if you denote the law of xt and yt by mu t, it is well known that this law must satisfy this linear Fokker-Planck type of equations. Well, it's this linear transport equation, actually. There is no diffusion. So there is a sort of linear transport equation where here as a transport field, you have really the field of the layers of the ODE. And so you can recast also the cost function that you saw before, this one. You can rewrite it in the sense of integrating mu t, the mu at a final time capital T, and you minimize the discrepancy between x and y, knowing that the dynamics for y is constant, you get exactly this minimization here. And this pairing of functional of this kind with the transport equations of this other kind has been called a mean field optimal control in the literature. And this is an issue that we have been discussing. In particular, we have been investigating how can we characterize the solutions of this optimal control problem in the sense of first order optimality conditions, whether this first order optimality condition called mean field Pontryagin maximum principle do admit unique solutions, and whether these solutions are stable. So they are, again, in a certain sense, a way to encode the input and output into these control weights. And it turns out that this is exactly the case. So if we have an optimal control, which is basically the weights of the network, then it must fulfill this maximum principle that is written here, where psi, if you want, is the dual variable or somehow the adjoint variable of the system, and the optimal control is characterized pointwise by this particular somehow fixed point equation that is coupling now both the forward and backward variables, so the primal and the dual variable. At the same time, as soon as you impose a little bit of regularization to the system, so you take some lambda parameter here sufficiently large, then it turns out that the solution is actually unique, and it is also smooth in time. So you get some smoothness of this optimal control. They are Lipschitz in time, and they are well behaved. And another point is that everything is quite stable with respect to the data, and the way to go is showing a sort of generalized Lagrange multiplier theorem on convex sets of Banach spaces, and then the existence of solution is based on Schauder or Banach fixed plus Banach fixed point arguments for the uniqueness, and that's more or less how it goes. As I said, stability gives you also some generalization error. So if you obtain by this particular ODE network a certain kind of empirical loss, then somehow the non-empirical loss, the true loss, won't be far away from that, up to the Wasserstein distance of the empirical measure of the input and output from the true probability measure distribution. So we do have this kind of stability result. Here is an example of a classification where there is a bunch of points that that first component positive should be classified with the 1, 1 vector, and those that have negative first component, they should be characterized with -1, -1 vector. And as you see, that's exactly what is happening. So there is a migration during the classification of the points. They are transported eventually to the corresponding labels, and that's an example of classification problem through this NeurODE. With this, I thank you for your patience. I kept it into 7 minutes, and I've been able really to deliver all the 3 tales, and nevertheless, I'm open to questions if there is any.